Okay, so we're ready to create a confidence interval for an unknown population standard deviation, sigma. And we'll be doing this by hand by finding a lower limit and an upper limit. And you'll see the chi-square values here that we just discussed with the table. And it says that our sample variance, S squared, is our best point estimate for the population variance, sigma squared. So I'm just going to repeat that, but with standard deviation, just to review the terminology again. So the best point estimate, so that vocabulary, point estimate, the best point estimate is the single number that we use to estimate a parameter. So the best point estimate for sigma is the sample standard deviation, S. All right, so we're trying to get an estimate for variation in a characteristic. And we're going to take this example of batteries. So it says lifetimes of AAA batteries are approximately normally distributed. So in order to use the process we're about to go through, we have to know that the variable itself is normal. So remember, a normal distribution is a bell curve. And though we could study the actual lifetimes of batteries, that's not what we're interested in here. Here we're interested in how much do these lifetimes vary. So are they a consistent product, or is there variation in how long the batteries are lasting? So that's what we want to find out. So a manufacturer wants to estimate the standard deviation. So that's variation in batteries, standard deviation of the lifetime of AAA batteries. So to do this, they take a random sample of 29 of their batteries, of the batteries produced by the manufacturer. And on average, their mean, on average, these batteries lasted 10.5 hours. And I'm just going to point out here that that was their sample mean. So we could use the sample mean to estimate the true population mean, but we're not doing that. We've learned to do that before. What we're doing today is learning how to estimate standard deviation. So for these 29 batteries, this was their mean. And then for the 29 batteries, the standard deviation came out to be 1.6 hours. So I'm just going to fill that in right now. So the sample standard deviation, S, our best point estimate for sigma is 1.6. I'm just going to add units so we know what we're talking about. So if the standard deviation had been 0, that would mean all the batteries are the same. They don't deviate at all. But we are seeing deviation in the sample, and we'll use this to estimate sigma. All right, so we have to first find these chi-square numbers, and they tell us we want to be 95% confident when we're done. And let's get our sample size here. So 29 batteries, so N is 29. So our degrees of freedom, N minus 1, so 29 minus 1 is 28. And 95% confident means we're trying to separate the middle 95% of the chi-square distribution from the rest. Alpha is 1 minus the confidence level. So 1 represents the whole graph. If you take away the middle, 0.95, you'll get the 2 tails. So we have 0.05 left in these 2 shaded areas. And then if we want each side separately, we take our alpha and cut that in half, divide by 2. And that tells us the area in each tail. And this picture is kind of small, so you can just point to these areas if you would like. So alpha over 2, 0.025. This is alpha over 2, 0.025. We draw pictures a lot as we complete this chapter and head into the next, where we're seeing these alpha over 2 numbers. But just a quick check here. Just make sure you understand all we're doing is separating the bell into 3 parts, the middle and the 2 tails. So when you add up those 3 areas, these areas all together better give you 1. So that's the idea here. So this number, chi-square alpha over 2, or you can just call it chi-square right. And this value, chi-square 1 minus alpha over 2, that you can just call chi-square left. So we find these numbers in our table. And to look up chi-square alpha over 2, we'll go to the table and look for this alpha over 2 value, 0.025. And then to find this value, we need to look up 1 minus alpha over 2. So 1 minus 0.025 is 0.975. So these two numbers are complements. Alpha over 2, 1 minus alpha over 2. And in your table, those complements you'll see are a pair of values. And I'm going to slide over to the table here. So 0.025 and 0.975. So on our table, think of this line down the middle. So here's 0.025. 0.025 is there. And you'll see I call it its partner over here, 0.975. So in the table is symmetric. I think the line down the middle. So these values are always complements. So when we look up numbers, these will be chi-square left numbers on the left side of the table. These will be chi-square right numbers on the right side of the table. And we have to come down to degrees of freedom 28. And then when I read across and down, it looks like 15.308 and 44.461. So chi-square left, chi-square right. All right, so let me add those to the picture. So 15, this is 15.308 and 44.461. All right. And again, I will draw the computer generated image here. And I know the print is a little small, but I can see a 15 there. So that looks good. And that one looks good. So there is our first step. So that's just getting these critical values. And now we're ready to create our confidence interval estimate. So our formula, it's the square root of n minus 1 times s squared. And that gets divided by chi-square. And I'm just going to point out here that when I wrote the formula, I used this notation, chi-square alpha over 2. And that is the chi-squared right value. So if you want to make it kind of simpler notation, you can just write chi-square on the right side. That's going to be our lower limit. And we're estimating sigma. And then the upper limit formula is n minus 1, s squared. The numerator is the same, but now the denominator will be the chi-square left number. So I'm going to substitute. Now we actually already found n minus 1, right? N minus 1, 29 minus 1 is 28. So I usually just put 28 since we already know what that number is. And then I don't need the parentheses. So I'm just going to type times. And then S was 1.6, the sample standard deviation, that gets squared. And then we divide by chi-square right, which is 44.461. And that's our lower limit. And then for our upper limit for the confidence interval, numerator is the same, 28 times 1.6 squared. and chi-square left, 15.308. All right, so for confidence intervals of a standard deviation, they are not symmetric. This curve is not symmetric, so we don't have another form. So unlike what we did with means and proportions, we don't have a margin of error anymore where we can say plus or minus. So I can't draw a picture of the confidence interval for you because the sigma that we're estimating based on this S value is not actually going to be in the center of the confidence interval. So we just write it in the form lower limit, upper limit as our estimate. Okay, so I'm going to just type that whole thing in at once. So square root 28 times 1.6 squared divided by 44.461. So you want to avoid rounding anything. So just type the whole thing in at once, and then we can follow the rounding directions that they say up at the top here. So round answers to at least 2 decimal places. So we'll go with 2 decimal places. So that's 1.27 less than sigma. And then our upper limit, and that is 2.16. So there's only one form, lower limit less than parameter less than upper limit. So on Alex, they might just ask you to say, what is your lower limit? What is your upper limit? And I'm going to complete the summary here that based on a sample of 29 AAA batteries, so using a sample to estimate a parameter, we are 95% confident that the true, so remember we're measuring standard deviation. So we're not estimating how long the batteries last. We're estimating the variation. So the standard deviation of all AAA lifetime batteries from the manufacturer, we believe, is between 1.27 and 2.16 hours. All right, so we will do confidence intervals for standard deviation by hand. We have our formula, and first step is to get those chi-square numbers and then substitute. So we'll do one where they actually give us the data rather than just giving us the sample standard deviation next.